Okay, so I've included for you a few things in PDF form. One of them, the guidelines for sketching a curve, which comes from the Stewart textbook. So he breaks down all these different steps, things you might look out for, and the guidelines are comprehensive, but you don't necessarily need to do all the things here in order to create a good sketch. It's just these are many of the things that can be helpful in creating sketches of a wide variety of functions. Okay. Something like finding the domain I would consider to probably be something you would always want to do. Intercepts would depend on how easy or difficult it would be. Y-intercepts, if they exist, are easy to find. You just plug in x equals 0. There can only be one y-intercept on any given function at most, one y-intercept. So those are easy to find, but the x-intercepts might be kind of complicated to find. Okay, but if they're not too bad to find, they could be very helpful to know. Asymptotes, I made this note over here. You might be able to, or you might need to, employ L'Hopital's rule in some cases when investigating asymptotic behavior. That's because all these asymptotes are defined where you use limits. Okay, and if a limit gives you, if the limit results initially in an indeterminate form, of which there are 7 indeterminate forms that we have seen recently, you can investigate that indeterminate form, the limit of that indeterminate form, right, through the use of L'Hopital's rule. We don't need L'Hopital's rule. We've looked at other approaches. We've seen algebraic approaches, even the use of some trigonometry in some examples as well, that allow us to investigate some limits. But L'Hopital's rule is a powerful tool that can allow us to investigate indeterminate forms, okay, when they arise. Okay? So it's another tool available to us. It's not a guarantee you're going to need it. It's just it's available to you if you're in a situation where it might be useful or convenient to do. All right, the intervals of increase, decrease, local maxima and minima. All right, first derivative use could be second derivative as well with maxima and minima. Okay, if the second derivative test is convenient to use, concavity and inflection, and then coming up with a sketch. And if you don't have enough information from all this that we've gathered so far, if you're still missing pieces of information, analytically about the shape of the curve or the direction it travels or something else, where it's positioned, you can plot extra points. So you can just plug in values from the domain into the function to find y coordinates to get some additional points in order to complete your sketch. Okay, so I've included Stewart's guidelines along with the note there about L'Hopital's rule. I've also included a worksheet, okay, with several of the things you might want to look for in order to be able to create comprehensive graphs of these functions, to be able to answer questions about what is the domain of the function, where do the intervals of increasing and decreasing, as we have done previously, create a reasonable sketch of the function, maybe labeling all the maxima and minima, whether local or absolute, as well as all inflection points. Also state the intervals of increase and decrease in the concavity, for instance. Investigate symmetry. Does this function have even symmetry, odd symmetry, or periodic symmetry, or does it have neither of these types of symmetry in it? Okay, so to be able to answer all types of questions about these functions, but not necessarily having to do all of these steps for every graph that you create. Okay, so I give you different types here. I give you a polynomial type here, a rational one here, as you should have seen in a previous, like a pre-calculus course. You should have investigated like rational function graphs. Take a look at it here. Here's another rational function type, and this one I put in here because it has a parabolic asymptote. All right, so recall that when we're looking at rational functions, if we wanted to know the end behavior as x goes to infinity or x goes to negative infinity, we can find that by taking the limit as x goes to infinity or negative infinity. Right, in a calculus course. In an algebra course, we say we can compare the degree of the numerator to the degree of the denominator. And if the degree of the numerator is greater than the degree of the denominator, then we at least know that there is not a horizontal asymptote. But in order to establish if there's some other type of asymptote, such as a slant asymptote, we can find it by doing long division. That is, we can do polynomial long division. In this case, we can divide x cubed by x minus 2. And if we do that, we're going to get something that is parabolic in shape. Okay, so a parabolic asymptote. A function like f of x is equal to x cubed over x minus 2 would have one of these. We could find it by long division, polynomial long division. X minus 2 divided into x cubed. Okay, now this would be truly x cubed plus 0x squared plus 0x plus 0. Okay, so I can have all the other terms. What do we multiply x by to get x cubed? We multiply by x squared, which I'm going to put over the x squared column. Multiply x squared times x minus 2, we get x squared minus, x cubed minus 2x squared, and then subtract from the line above. So we have 0x squared minus negative 2x squared. That leaves us with 2x squared. Now we can continue with the division. Multiply x by 2x to get 2x squared. Then 2x times x minus 2 is 2x squared minus 4x. Let's bring down this plus 0x, and then let's subtract this product we just found. So these cancel. 0 minus negative 4 gives us positive 4, and I'm going to bring down the next plus 0. Multiply x by 4 to get this, so we get 4 times x minus 2. That's 4x minus 8. We can subtract. 0 minus negative 8 is positive 8, and that's going to be a remainder because the degree of this, okay, the degree of the remainder, which is 0, it has degree 0, is less than the degree, okay, of x minus 2, because the degree of x minus 2 is equal to 1. As soon as the quantity we get here after subtracting, as soon as its degree is less than the degree of what we're dividing by, we know we have a remainder. So f of x equals x cubed over x minus 2 can be rewritten as the sum of this quotient x squared plus 2x plus 4 and the remainder divided by the original denominator x minus 2, right? So this is a rewriting of the original function. Now if we take the limit, okay, if we take the limit as x approaches infinity of f of x, okay, that limit is going to infinity overall, okay, but it in fact is also, it is approaching this because the limit of this right here, as x goes to infinity, the limit of this would just be 0. Okay, so the limit of f of x as x goes to infinity is equal to the limit, okay, is equal to the limit as x goes to infinity of x squared plus 2x plus 4. The reason I've removed this again is because the limit of this term is just 0 as x goes to infinity or negative infinity. So our function and this quadratic right here are approaching each other as x gets very, very large. That means that this is therefore an asymptote. Okay, so y equals x squared plus 2x plus 4 is an asymptote for the function f of x, and the shape of this asymptote is parabolic because it's a quadratic function. So this is a parabolic asymptote or a quadratic asymptote. Okay, so now we know the end behavior of this particular function. Okay, so that's helpful for us in constructing a graph. Okay, so just the graph of this asymptote, we know that it has a point on it. Let's see, when x is equal to 0, that's y of 0, that's equal to 4. Right, so y of 0 is equal to 4. We know that the leading coefficient is positive, so this is a face-up parabola. Okay, so we have a point here at 0, 4. This is not a point on the curve for f of x necessarily. This is for the asymptote. Okay, and we also have, let's see, the vertex of our asymptote, negative b over 2a. That would be what, negative 2 over 2 times 1, which is negative 1. And y of negative 1 is going to be 1 minus 2 plus 4, 5 minus 2, which is equal to 3. So we have at negative 1, 3. Okay, sorry, okay, there you go. This is 4. Okay, at negative 1, 3, okay, we would have the vertex, okay, for our parabola here. And so if it crosses through 0, 4, and by symmetry, it would also exist over in this direction, okay, because right, quadratics have symmetry about the imaginary line that would go through their vertex. And so this is the asymptote. So we'll come back to this example in a moment. Again, we can complete the graph. Now, the other thing that I've included for you here are my typed notes that I constructed for you. We should start with that first and foremost. Okay, I give you the objectives of the section, and I give you my introduction along with some examples. Here's an example where I talk about graphical addition. And graphical addition is where if you take the y coordinates, okay, for along two curves with the same x value, okay, the graph of the sum of those two functions would have a y coordinate equal to the sum of the two y coordinates. Let's say we wanted to graph the sum of a linear function with a rational function, something like a times x plus b over x squared. Well, if we were to sketch the graph of each of these terms, okay, I've graphed here y equals a times x, right? It's a line that goes through the origin. If a is positive, then it has a positive slope. So this is the graph of y equals ax, which is the first term here in the function. And b over x squared would be a rational function. It would have a vertical asymptote where x is equal to 0, for instance. Okay, so that is the graph of this blue function here. Okay. If we wanted to graph f of x, which is the sum of those two, we could say, well, for any x value in the domain of f of x, we could take the y coordinates for that x value from the other two curves and add them together. So, for instance, if I wanted to know what is the y coordinate for f for this value of x right here, whatever that value of x is, we could look at what the associated y coordinate value is on the blue curve and the y coordinate on the red curve for that same x value. Add the two y coordinates together to get the y coordinate on our function. On this side, where we see that we have that the red line goes south of the x-axis, but the blue is north of the x-axis, right? Again, you can see that if we take, let's say, a value like x right here, we can take the y coordinate from the blue curve, which is right here, which looks like a relatively small positive number, and the y coordinate from the red curve right here, which is a larger in magnitude negative quantity. And if you take a small positive number and add a larger magnitude negative number to it, you're going to end up with an overall negative quantity. So the y coordinate on the black curve here can be found by adding together the y coordinates on the blue and the red functions. Okay. It can be a useful strategy for things such as, how about this? F of x equals x plus sine of x. And we know how to graph y equals x. We should know that from beginning algebra course. And we know how to graph y equals the sine of x. We should know that from trigonometry. So each of those graphs independently are not that difficult to sketch. But the graph of y equals x plus sine x, that's a new, more complicated graph. Well, here's how we could do it through the use of graphical addition. The graph of y equals x I've shown here in red, right? And the graph of y equals sine x I've shown in blue. Now, any point on the black curve can be found by adding together the y coordinates on the red and blue curves. All right? So for instance, what would be f of pi? I mean, we could evaluate that directly, but how can we use graphical addition to find that? We take x is equal to pi, we can evaluate what's the y coordinate from the blue curve, in this case it would be 0, and what's the y coordinate from the red curve, which would be pi. And if we add 0 and pi together, those two y coordinates, we get the y coordinate on the black curve. If we go out to a value like, how about we go out to 3 pi over 2? If we take the y coordinate on the blue curve at 3 pi over 2, we see we get a negative quantity. In fact, it's -1. And on the red line at 3 pi over 2, we get a positive quantity. It would be 3 pi over 2. So the associated y coordinate on the black curve is the sum of those two y coordinates. That's 3 pi over 2 minus 1. And that would be the y coordinate right here. It would be 3 pi over 2 minus 1. All right, so investigating extrema, let's look at the first derivative. Okay, the domain is all real numbers. It's not a closed interval, so we should look within that open interval through the use of the derivative in Fermat's theorem. In addition to checking where the first derivative is equal to 0, we also want to see where the derivative might not exist, if anywhere. Well, this derivative is 1 plus cosine x. That's the derivative of x plus sine x. And that exists for all real numbers. So the critical values will only be where this is equal to 0. And this is equal to 0 where the cosine of x is -1. And that occurs in an infinite number of locations. It occurs at all odd multiples of pi. right? For example, cosine of pi is -1, but also the cosine of negative pi is -1, and the cosine of 3 pi would be -1, etc., etc. So all of these quantities would therefore be critical values for the original function f of x equals x plus sine x. These are going to be the values, okay, the odd multiples of pi are going to be the values where the original function would have horizontal tangent lines. Let's take a look at that curve again. So we have a horizontal tangent line where x is equal to pi. Looks like it from the curve. We have a horizontal tangent line where x equals 3 pi, the next odd multiple of pi. Looks like it. At negative pi, right there, and at negative 3 pi. And this would continue by periodicity. This is going to continue. All right, now we can determine are any of these local maxima or local minima. How can we do that? We could use either the first derivative test or possibly a second derivative test. Now, the second derivative test, it looks like it might be convenient for this because the second derivative is not that difficult to find. But the second derivative of this is negative sine x, right? And the second derivative test is to plug the critical values into the second derivative. If you plug the critical values into the second derivative, that is the critical values we found from the first derivative, if those then get plugged into the second derivative, if the second derivative is either positive or negative, then we know we have a max or min. But what happens if the second derivative is equal to 0 at the critical values? Which is going to be the case here. Negative sine of x, if we evaluate that at some place like pi or 3 pi or 5 pi, any odd multiple of pi, okay, then we're going to get that the second derivative is equal to 0 there. And if the second derivative is equal to 0, it is inconclusive from the second derivative test. It gives us no conclusion. We saw previously in a previous section where the second derivative might equal 0, where you have a maximum, a minimum, or an inflection point. All are still possible. So for this function, to determine whether we in fact have maxima and minima, we would really need to use the first derivative test. And that's essentially testing for increasing and decreasing nature around the critical values. So we're going to plug in values on the subintervals of the domain, of which there's an infinite amount of these, okay? But we do have a periodic portion of this function, and so that's going to help us here as well, okay? So we take a look within the subintervals, and we find that for any value we plug within these subintervals, right? So I'm not plugging in the critical values, I'm plugging in values that are within the subintervals between critical values, and finding that the first derivative ends up being positive within each of those subintervals. So we have a function that is increasing, and then it goes flat at the critical value, at a critical point, and then it increases again, and then it continues with that behavior. Okay, so none of these critical values are either maxima or minima. We have no local maximums, no local maxima, no local minima. We also know that we have no absolute maxima and no absolute minima. Why? Again, we can take the limit of this as x goes to infinity and find that the limit of this is going to infinity. The limit as x goes to infinity of this we can do term by term. Now x would be going to infinity, but the sign of x, remember, fluctuates between positive and negative infinity. So the limit of the sign of x as x goes to infinity, that limit by itself does not exist, but it is bounded. That is, the limit of x plus sine x is bounded between x plus 1 and x minus 1. All right, we take the limit as x goes to infinity of x plus sine x. Okay. Well, the limit for the sine of x, that one's not going to exist. Okay, does that mean this overall doesn't exist? Well, what we know is we have boundedness of the sine function. Since the sine of x is bounded between -1 and +1, then x plus sine x is bounded between x minus 1 and x plus 1. Okay? So the limit of this is bounded between the limits of these two. Right? So the limit as x goes to infinity of x plus the sine of x, okay, is bounded between the limit as x goes to infinity of x minus 1 and the limit as x goes to infinity of x plus 1. And each of these limits are going to infinity. Okay? So therefore, our limit is also going to infinity. Okay, and then if we went to negative infinity, by the way, right, if we took the limit as x goes to negative infinity of x minus 1 and x goes to negative infinity of x plus 1, okay, then our limit as x goes to negative infinity of our function is bounded between those two as well. These are each going to negative infinity. So therefore our function is going to negative infinity as x goes to negative infinity as well. So our function is going up into quadrant 1 off to infinity, and off into quadrant 3, negative infinity. Okay, x goes to negative infinity, y also goes to negative infinity. So there are no absolute maximum. There's no absolute maximum and there's no absolute minimum for this function as well, if that was something we wanted. Okay. Inflection points and concavity. How can we find it? Second derivative. So we can take the second derivative, we can find the critical values for the second derivative. That's where does the second derivative equal to 0, or where does it not exist? Well, this particular second derivative exists for all real numbers, so we're only interested in where it equals 0 then to determine concavity. We set it equal to 0, we find that if we have all integer multiples of pi, for the cosine was equal to -1 at the odd integer multiples of pi, but the sine of x is equal to 0 at every integer multiple of pi. So that's 0, pi, 2 pi, 3 pi, 4 pi, and negative as well. Negative pi, negative 2 pi, so on and so forth. So then we want to test around these values within subintervals. So we can subdivide the domain up for all the multiples of pi, the integer multiples of pi, and then we can choose test values within each one of those subintervals. Okay? So for example, we get negative 3 pi over 2, which is between negative 2 pi and negative pi. And we find there that the second derivative would be negative, so hence it's concave down on the interval between negative 2 pi and negative pi. How about between 0 and pi? Between 0 and pi, we can choose a value like pi over 2. Plug pi over 2 into the second derivative to test concavity, and we get negative, okay, for the output to second derivative there. So therefore, the function is concave down on the interval containing pi over 2, and that would be the interval from 0 to pi. All right, so it is switching from concave down to concave up, concave down, concave up. Okay, so we have many, many inflection points. There we go. So we have many inflection points because we have points that are contained within the domain of the function, so these points exist, and we have the concavity is changing over those points, so we have lots of inflection points. Okay. And below is a graph which includes the intercepts, the local extrema, which there were none, and the inflection points. All right, so that's a pretty comprehensive graph there. Okay. Now, before we move on to this next function here, I want to go back to this example right here. Let's create a more comprehensive sketch for this. F of x equals x cubed over x minus 2. This is one that comes from the worksheet as well. We know that it has a parabolic asymptote. Okay, let's come up with a sketch for f of x is equal to x cubed over x minus 2. This sketch, let's include the asymptotes. Okay, let's include maxima and minima. Let's also include inflection points. That is, we would need to look at concavity to determine if there are any inflection points. Okay. All right, that should be good for this one. Okay, I'm also going to include intercepts if they're easy enough to find. Okay, so let's find that. Okay, first, domain. The domain would be interesting to have. We have that the numerator exists for all real numbers. The denominator is also polynomial, but the denominator can't be 0. So x minus 2 is not equal to 0. Therefore, the domain of this function, okay, is that x is not equal to 2. Or we have negative infinity to 2, open, union, open from 2 to infinity. There's a domain of the function. So we have a break in the domain. Anytime we have a break in the domain, we should investigate to see if we might have asymptotic behavior. How we investigate asymptotic behavior in the calculus classroom is through the use of a limit. So we really would want to be looking at the limit as x goes to 2 from the left of f of x, see what that equals. Okay. And we want to take a look at the limit as x goes to 2 from the right of f of x and see what that equals. So we have x cubed over x minus 2. If we take x to approach 2 from the left, imagine choosing values that are a little bit less than 2. Well, then x cubed is going to be approaching, okay, then x cubed is going to be approaching like 8, but it's going to be a little bit less than 8. Okay? And the denominator, which was x minus 2, x is approaching 2, so x minus 2 is approaching 0, but how is it approaching 0? Well, we have x is in fact a little bit less than 2 right now, like 1.999. And if we subtract 2 from that, we're going to get a number that's a little bit less than 0. So the denominator is going to 0, but it's just a little bit negative, and that's important. So we have a positive, right? We have a positive quantity on top. It's a fixed, right? It's a finite value, really close to 8. It's positive, and it's being divided by what is a negative but very, very small number in the denominator. So this is going to a very large in magnitude quantity that's ultimately negative, so this is going to negative infinity. That means we have a vertical asymptote, because at least one of these two is going to either positive or negative infinity. There must be a vertical asymptote, therefore, at x is equal to 2. The limit as x goes to 2 from the right, we're going to get the numerator, which was x cubed, is going to be approaching 8, but it's a little bit more than 8. Okay, and the denominator, we have a number a little bit more than 2. Subtract 2 from that, we're going to get a number that's close to 0, but is still a little bit positive. So we get a positive divided by a positive, right? But the numerator is a finite value, but the denominator is very close to 0, very, very small. So this ratio will be very, very large, but positive. Okay? Again, indicating that we have a vertical asymptote. Okay, so we know that the graph is going to have a vertical asymptote at x equals 2. We also know that the function from the left is approaching this asymptote by going down, and it's approaching this asymptote from the right by going up. Okay, so we know something about the behavior and the shape of this curve. Okay. Other asymptotes: horizontal, slant, okay, so on and so forth, found by taking the limit as x goes to infinity of f of x and the limit as x goes to negative infinity of f of x. All right, and that's where we get x minus 2 into x cubed, and we end up with that expression x squared plus 2x plus 4, okay, telling us that we have a parabolic asymptote. Okay, there was a remainder here, right? It was plus 8 over x minus 2. So the parabolic asymptote has equation y equals x squared plus 2x plus 4. And so now we can include that on our graph as well. Okay, something parabolic, and that's asymptote right there. Now, our curve might fit within this region right here, but we shouldn't assume that yet because we don't know if it crosses the asymptote, and it might. It might cross the asymptote. It could, for instance, do something where it goes through and then comes back like this. Those types of things happen in graphs sometimes. So let's establish whether we might cross our parabolic asymptote. Okay, let's see. Does f of x cross or intersect, okay, the parabolic asymptote? How can we determine whether the graphs of two functions intersect each other? By setting the rules of the functions equal to each other. Let's take x cubed over x minus 2 and set that equal to x squared plus 2x plus 4 and see if we get any solutions to this equation. Then if we get values of x that solve this equation, then we know at those values of x, which we can then find the associated values of y, we would know that the graph and the asymptote are in the same location. So we can multiply by x minus 2, right, to the other side. We already know that this is not exactly equal to this, right, because there was a remainder. Okay, so we can multiply this out. So we get x cubed now is equal to, let's see, we got x cubed here. I'm going to get minus 2x squared, and then there's a plus 2x squared, right? So this times this is minus 2x squared, and this times this is plus 2x squared. Those will cancel each other out. And then 2x times negative 2 gives us a minus 4x, but then 4x times x gives us a plus 4x, and those will cancel each other out. And then we can multiply 4 times negative 2, and we end up with negative 8. So we have x cubed is equal to x cubed minus 8. Well, now we can subtract x cubed from both sides of this equation, and we get 0 equals negative 8. But that's false. That's a false statement, and so it doesn't mean we did something wrong. It means the answer to this question here is no. Does our function cross the asymptote? No, it does not. Well, what does that tell us then? If we already have that the domain of the function is all real numbers except for 2, and now we have that the function is approaching the vertical asymptote like this, it has to approach this parabolic asymptote as x goes to infinity. It either approaches it from above or below, but we now know because it's not allowed to cross this function, we just found it doesn't cross it, it has to approach it from above. So most likely right now this is going to curve around like that. But does it have to exactly look like that? Not necessarily also. I mean, we still don't know. We know that it approaches from above because it can't approach from below. But we don't know if in the middle, if it does do something like that. Right? Does it have it? How do we know? We could look at, is it increasing versus decreasing? We could look at concavity and inflection in order to determine if it is, right? If it is simply just going to curve around, is it all concave up, for instance, in this region? Or is it go from concave up to concave down? If it went from concave up to concave down, we would have another feature to have to put into here. So we have to determine if that's true. Now we also know, by the way, the function approaches the vertical asymptote from the left like this, and we know it has to approach the parabolic asymptote either from above or below over here. And we just found that our function does not cross the parabolic asymptote, and there's no other breaks in the domain, like it can't just disappear and then show up here all of a sudden or something like that. Okay? It is otherwise continuous, since this is a rational function, there's no other breaks in its domain. So the only way for it to approach this asymptote then, without crossing it, is that it must be approaching it from below. So it has to go like this. Alright, it has to get closer and closer to the function, like that. Now, does that mean that it just smoothly goes through something like that? Possibly. It could also do some other kinds of stuff out here as long as it's still a function. It could do some stuff like that. And we would be able to find out the shape of the curve, again, by investigating concavity, as well as increasing and decreasing. So that's something we should be looking at. So we've included the asymptotes now. Okay. Let's look at maxima and minima, and let's look at inflection. So maxima and minima. Well, it looks like already, since we did this analysis of the vertical asymptote, it's going to infinity, it's going to negative infinity. So we already know that it has no absolute max, and it has no absolute min. But we can still look to see if it has local maxima or local minima. Okay, so let's find the first derivative, f prime of x. So the derivative of x cubed over x minus 2. Okay, so quotient rule will work here. So we get x minus 2 times 3x squared minus, right, so we have low d high minus high d low. So we have x cubed times the derivative of x minus 2, that's 1. Don't forget to square below. So we square the denominator, so we get x minus 2 squared. Okay, so where does this not exist? First of all, right, f prime of x does not exist at x is equal to 2. But x equals 2 is also not in the domain. All right. Okay. X equals 2 is also not in the domain of f. Okay. All right. So, okay. So we don't have to investigate it as if it was like a maximum or a minimum. It can't be a maximum or a minimum point because it doesn't even exist on the curve at that point. But we want to see maybe where this is equal to 0, so let's go ahead and simplify this a bit. X minus 2 times 3x squared minus x cubed. I'm going to factor out an x squared from that. So I take out x squared. That leaves us with 3x minus 6 minus x. All right, because I pulled out an x squared from here and an x squared from here. So 3 times x minus 2 minus x. All right, and then we have x minus 2 quantity squared. So this is x squared times 3x minus x is 2x, right? So 2x minus 6, and that's over x minus 2 quantity squared. Okay. So find out where the numerator is equal to 0. If the numerator happens to equal 0 where x is equal to 2, we can remove one of those factors. Otherwise, anywhere where the numerator is equal to 0, we'd want to investigate those as critical values. So we have f prime of x is equal to 0 at x equals 0 and at x equals 3. Right? So these are the critical values then for us to consider. If we're doing increasing and decreasing, though, we should test around where x is equal to 2 as well. Okay, maybe that's something we should end up doing anyway. But these are the potential locations of the maxima and the minima. Okay, so let's test that as well as these in establishing where this function is increasing or decreasing. All right, so x, okay, we're going to look at f prime. Okay. Let's see. Let's take out where x is equal to 0. We'll take out x is equal to 2 as well in order to investigate, again, where it's increasing and decreasing. Does not exist here. That is f prime does not exist here. F prime, okay, is 0, so it's flat here, and it's 0, so it's flat here. Okay, let's test within these intervals, sub-intervals, like at -1, +1, 2.5, and 4. Let's see what happens. F prime of -1, for instance. Here's our f prime right here. F prime of -1, I'm going to get a positive, because -1 squared. And then we get 2 times -1 is -2 minus 6. That's going to give us a negative. And the denominator, notice, no matter what real number we plug in, this is going to be positive. Okay, unless it's, except for 2. Okay, we're not plugging in 2 though. Okay, so we get negative over positive. This is overall then going to be negative. So on the subinterval here, okay, where -1 is contained, we have that the function is decreasing. Okay, and then it becomes flat. Next subinterval at 1, let's test f prime of 1, increasing or decreasing. Well, x squared, that's going to be positive. Again, squaring a real number, you're going to get non-negative. It's either going to be 0 or positive, and this is positive. And then we get 2 minus 6, which is negative, and the denominator is positive. So we have overall negative. So the function is also decreasing on the interval, the open interval, from 0 to 2. Let's test at 2.5. So f prime of 2.5, we get positive. For the first factor of the numerator, positive for the denominator. And if x is 2.5 here, we get 2 times 2.5, which is 5, minus 6, which is negative. So we get negative. We get that this function is also decreasing from between 2 and 3. And finally, how about greater than 3, from 3 to infinity? Let's test at 4. So f prime of 4, okay, we get positive for the denominator as well. And 2 times 4 is 8. 8 minus 6 is 2, so that's positive. So we get overall it's going to be positive. The first derivative is positive on the open interval from 3 to infinity. So the function is increasing there. Okay. So we have that f is decreasing on the intervals, let's say, -infinity to 0. That's open. And the open interval from 0 to 2. And the open interval from 2 to 3. Okay, we have that f is increasing on the open interval from 3 to infinity. Okay, so I'm going to include that information on the curve. What does this tell us about maxima and minima? This point right here is neither a maximum nor a minimum. Neither max nor a min. But this point right here would have to be a local minimum. We already established there is no absolute minimum, right? But this would have to be a local minimum. So the local minimum exists where x is equal to 3. Where x is equal to 3. All right? So what's the value of the function where x is equal to 3? Let's find that. So that's f of 3, which is equal to 3 cubed over 3 minus 2, and that equals 27. Okay. All right, so that means that 327, okay, is the local minimum for the function. All right, so I'll create a better sketch in a moment, but so we found that there is no minimum, no maximum anywhere, okay, over here. So we know that the function is not going to be able to do something like this, for instance, because then there would be a local minimum somewhere over here. Okay, so it's not going to have that shape, but it still could kind of do stuff like this, where it never really has a minimum in it. In fact, where the derivative is never necessarily equal to 0, and it still might wave around. How would we know if it sort of undulates like that? We should look at concavity, because if it did something like this, we would have that it was maybe concave down up into a point like around here, and then it became concave up to maybe around here, and then concave down again, and then concave up. So the concavity would change if we had some sort of a graph that was kind of waving back and forth like that, and we should look into that. But we do know that the function at where x is equal to 3, so if 3 is somewhere out here, we know that it's going to min out. There is going to be a minimum, and that's the only place on the curve whereby the tangent line would be horizontal. So it seems reasonable we might have a function that does something like this. But again, it could do some kind of waving around in here, and we should look at concavity in order to establish whether that happens, even though it doesn't have to have another maximum or minimum in there. Okay, let's continue then with our function. We had a derivative right here, x squared times 2x minus 6 over x minus 2 quantity squared. And now let's go ahead and see if we can find the second derivative to investigate concavity. Okay, so we had f of x was x cubed over x minus 2. F prime of x was x squared times 2x minus 6 over x minus 2 squared. I could also factor out a 2. 2x squared times x minus 3 over x minus 2 quantity squared. Okay. Let's find out what f double prime of x is equal to. Okay. Right. To find that, in fact, I'm going to expand this, because then we can do the derivative of the numerator. We can do it term by term within our quotient rule, because if we left it like this written as a product, we're going to have to do a product rule inside of the quotient rule. Okay. So I would prefer to expand this then. So we have 2x cubed minus 6x squared over x minus 2 quantity squared. All right. So the second derivative. So we have x minus 2 squared, that's low d high minus high d low. So x minus 2 squared times the derivative of the numerator, which will be 6x squared minus 12x, minus the numerator, 2x cubed minus 6x squared, times the derivative of the denominator, which is 2 times x minus 2 to the first times 1, just to say that the chain rule is really being used here, just in case there was something else in there for us to take the derivative of beyond just that linear piece with a derivative 1. The denominator then gets squared, so we have x minus 2 to the power of 4. Okay, now want to determine where does this not exist? Where is this equal to 0? Well, f double prime of x, again, does not exist at x is equal to 2. So we're going to want to look around that for intervals of concavity. But this is not a point on the curve because it's not in the domain of the function, so it's not an inflection point. Okay? Clearly that's not an inflection point. Okay? Since f itself does not exist at x equals 2. Alright. Okay, so I'm going to clean this derivative up here so we can set it equal to 0. So we have 0 is equal to, let's see what we got. I could factor out a 6x from here. So take out 6x. We have x minus 2 squared, but then this leaves behind x minus 2, another x minus 2. So this is 6x times x minus 2 cubed. All right, because 6x times x minus 2 is 6x squared minus 12x. Okay, minus. We can factor out from these two terms a 2x squared, and I can take out a 2 from here. So I'm going to take out a 4x squared. Let's see, taking out a 2x squared from here would leave us with an x minus 3. X minus 3, and then we also have x minus 2 from here. Okay, the denominator is x minus 2 to the 4th. So I see we have a shared factor of x minus 2. All right, we have 3 of them here, we have 1 of them here, we have 4 of them here. So I'm going to cancel out a single instance of x minus 2. So we have now 6x times x minus 2 squared minus 4x squared times x minus 3. over x minus 2 to the fourth. Now, the numerator does not equal 0 when x equals 2. The first term does, but the second term does not equal 0. So the numerator does not have a factor of x minus 2. This is x minus 2 to the third in the denominator. So, since the numerator does not have another factor of x minus 2, there's no removable discontinuity type here. We can find the zeros then by just setting the numerator itself equal to 0. Right? Just as a reminder, right? If the numerator is equal to 0, but the denominator is equal to 0 at the same value, then in fact there's a removable discontinuity there, right? Which is still something to consider, okay, when we're testing around, but we're already testing around x is equal to 2. Okay, but it's a different kind of a graphical feature, of course. Okay, anyway, so solving this equation, I'm going to do this by expanding here. So we have, let's see, x minus 2 squared, quantity squared is x squared minus 4x plus 4. And then we have, what is this, minus 4x cubed plus 12x squared. In fact, we can factor out a 2x from both here and here. I'm going to take out a 2x. That would leave behind a 3 here. So we have 3 times x squared minus 4x plus 4. I've taken out a 2x from here, so this is leaving us with a minus 2x squared, and from here a plus 6x. So 2x times, let's see, we got 3x squared minus 2x squared leaves us with x squared. Right? Minus 12x plus 6x is minus 6x. And then 3 times 4 is 12, so this is plus 12. Okay, so we're setting these equal to 0. 2x is equal to 0 when x is equal to 0, so that's a value to test around. This potential inflection point, because it is in the domain of the function. The function's continuous there. And where x squared minus 6x plus 12 is equal to 0, we want to check that as well. Does this factor? 4 and 3 doesn't work, 2 and 6 doesn't work, 1 and 12 no. So how about the quadratic formula? Let's check the discriminant. B squared minus 4ac, which in this case would be 36 minus 4 times 1 times 12. Okay, 4 times 12 is 48, so 36 minus 48, which is negative 12. That's negative, so this has no real solutions. Okay, so the only quantity here that's a potential inflection point location is where x is equal to 0. But we also have x is equal to 2 as a critical number of the second derivative to test around if we're interested in concavity. Okay, and I am interested in concavity, so 0 and 2 are going to subdivide, or subdividing the domain into 3 subintervals then, and we're going to be testing the second derivative within these subintervals. So 0 and 2 are the critical numbers of the second derivative, but 0 is the only one that could potentially be an inflection point. 2 is where the second derivative did not exist. In fact, the function didn't even exist there. But we still have to test around it for concavity. So let's choose test values. I'll choose negative 1, I'll choose positive 1, I'll choose positive 3, and check for concavity in order to establish where we have inflection. Starting with the second derivative at negative 1. And what is our second derivative? We just simplified the numerator down to this. I'm going to take that divided by the denominator was x minus 2 cubed. Okay, let's place that over here. F double prime of x, okay, is equal to 2x times x squared minus 6x plus 12, and the denominator is x minus 2 cubed. So let's plug in negative 1. We're just checking for signs here. 2x would be negative when x is negative 1. Okay. All right, 2 times negative 1 is negative. X squared minus 6x plus 12. Okay, I'm going to do a graphical analysis piece on here. X squared minus 6x plus 12. Let's take a look at its graph real quick, because it's going to make it really easy for us to determine whether this is positive or negative at all these quantities. This is the graph. This has the graph of a parabola. The leading coefficient is positive, so it's a parabola that opens upwards. It opens upwards. Where is it positioned? Well, we know that its y-intercept is at positive 12, and furthermore, what we also know is that the function is never equal to 0 for any real numbers. That is, graphically speaking, then, our parabola does not cross the x-axis. It has no x-intercepts. No x-intercepts, because there are no real solutions to setting this equal to 0. So it's opening upwards, it goes through this point, right? It has no x-intercepts, okay? And furthermore, we can even find out, well, let's find out, to which direction would we find the vertex. Negative b over 2a is equal to positive 6 over 2, which is equal to 3. So its vertex is found on this side in quadrant 1. So the graph of this parabola, a quick sketch of it is like this. This tells us that the function is greater than 0, okay, for all x values, okay, for all real numbers x. So that means this factor right here, for all of our test values, -1, 1, and 3, or any other number we might choose, this factor is going to be positive for all of them. Okay, so now we don't have to actually plug those numbers in to find out what the quantity is. The denominator is, when x is -1, the denominator would be negative cubed, which is negative. So we have overall a negative divided by negative, which is positive here. So the second derivative is going to be positive on this subinterval. So it is concave up, therefore, on that subinterval. Now let's check the next, right, critical number of the second derivative. That's at 1. So f double prime of 1, okay, so 2 times x would be positive there. 2 times 1 is positive. We just established that this is going to be positive for all quantities we plug in. And the denominator 1 minus 2 is negative, and a negative cubed is negative. The second derivative is negative at 1. Therefore, the function f is concave down on the interval, open interval from 0 to 2. That means we have a change in concavity happening at 0. Therefore, we can label this as an inflection point when x is equal to 0. Okay, we can go back to the original function to find out what f of 0 is equal to in order to find the associated y-coordinate. Alright, and then finally, let's test our second derivative at 3. 2 times 3, that's positive. Okay, this quantity, again, positive. And 3 minus 2 is positive. Positive cubed is positive as well. So we have the second derivative is positive at 3. So we have that the function is going to be concave up on the interval, open interval from 2 to infinity. Even though we have a change in concavity, we do not have an inflection point at 2 because we don't even have a point at 2, right? It's a vertical asymptote there. The function didn't exist. But we do, in fact, have one inflection point. Okay, so the graph has an inflection point at 0, f of 0. Now, what is f of 0? The function was x cubed over x minus 2, so that's 0. So the inflection point is located at the origin. Okay. So we can include that on our graph. And we also have information about concavity. It goes concave up to concave down to concave up again. Okay, so we'll try to improve upon our sketch over here. All right, so we had that the function now has an inflection point right here. There's inflection point. We had that the concavity, right, was going from, it was concave up, and then it was concave down within this region from 0 to 2, and then it went back to concave up again. No other changes in concavity on like this piece right here. And if it's only strictly concave up, then we don't have any of those, any kind of undulating waves going on or any of those features in there. Here we have that this graph is supposed to be concave up throughout, so it's nice and smooth, concave up throughout. It hits an inflection point right there, and then it turns to concave down. Okay, so it's nice and smooth like that. Okay, so there's a little sketch for our curve. For a more detailed sketch, I included this one on your worksheet. Here you go, here's the answers to your worksheet. Well, the graphical answers, not all the detail of all the different features and everything, but this letter C right here is the one that has the parabolic asymptote. It also has a vertical asymptote. It goes right through x equals 2. There's a nice smooth portion of the graph up here, a nice smooth portion right here. We see inflection happening at the origin, so it goes from concave up to concave down. How about increasing and decreasing? This function is decreasing from negative infinity to 0. It's flat at 0, and then it's decreasing from 0 to 2, right? It was decreasing, flat, decreasing. Then it was decreasing until x is equal to 3. At 327, we had a local minimum. So decreasing, inflection, decreasing, asymptote, decreasing, local minimum, and finally increasing, approaching our parabolic asymptote. Okay? And all that, we found all that corresponds with what we found here when we look at increasing and decreasing. It was decreasing, flat, and then decreasing. Then we hit that asymptote. On the other side of the asymptote, it was decreasing. We hit a local minimum, and then it was increasing. And we had all that, the features of concavity shown on that graph as well. Okay. All right, so that was a good rational example that had a parabolic asymptote in it. Okay, had a lot of interesting features. It had inflection, all that stuff. Okay. We've taken a look at one that had a vertical tangent in it, I believe, before, a couple sections ago, when we were dealing with the local minima and maxima and critical values, for instance. Okay, letter D, you can try that one out, see if you can come up with a sketch for that, see if you can find a variety of the different features described here. Increasing and decreasing intervals, concavity, how do you locate inflection points, how would you locate if there's any asymptotes there. And how would you investigate whether there's a vertical tangent? Take the derivative. If at a vertical tangent, recall that the slope of the tangent line would be undefined. We can see that symbolically by taking a look at the derivative of the function. If the function is defined at that point where the vertical tangent is, but if the derivative would approach infinity, okay, in the sense of if you take the limit as x approaches that value. Now notice that the domain of this function now is going to be all real numbers. It's polynomial times a cube root. The domain is all real numbers. It exists everywhere. But the derivative of something like a cube root is going to push the cube root to the denominator. By the power, think of the power rule. X to the 1/3, the derivative, you're going to get 1/3 x to the negative 2/3. So you will have, with a negative exponent, you would have an instance of a cube root showing up in a denominator. So we can expect that x is equal to 0 is going to be a value that is not in the domain of the derivative for this function. Even though x is equal to 0 is in the domain of the function itself. Right? If x is equal to 0, we get 0. So the point 0, 0 is on the curve. But the derivative at 0 would not exist. Now, if the denominator contains a factor such as the cube root of x in it, okay, we should be investigating the local behavior around that, like we would with asymptotes. We can take the limit as x approaches 0 from the left and the limit as x approaches 0 from the right. I'm talking about with respect to the derivative itself. Okay, if you take the limit of the derivative as x approaches 0 from the left and the right, for this example, look at this graph here. So if you take a look at the slopes of the tangent lines, as we get closer to 0, the slopes of the tangent lines would be approaching negative infinity. All right, so approaching negative infinity, so there would be a vertical tangent there. Looks like we're going to find that this function is decreasing when x is less than 0. It looks like it's going to be decreasing as well between 0 and whatever value we would find for what looks like a local minimum here. Okay, and then it's going to be increasing from that value x for the local minimum, all right, out to infinity. We see concavity here. It looks like this is concave down for x is less than 0, and it looks like it is concave up for x is greater than 0. So we want to make sure that we can find out and confirm if that's true, all right, by looking at the derivatives, all right, and doing subintervals. It could even be true that from the picture I have here, it's difficult to tell what the concavity really is here. If it could be very subtle that it changes, but we'll know for sure, right, by analyzing the second derivative what the concavity really looks like out there. All right. Certainly advantages to looking at a graph in that we can see so much information collectively in such a small amount of space, but we can get really detailed analytical information, okay, by looking at the actual the function symbolically, including its derivatives. Okay, this function right here, we would get an indeterminate form where, if we took the limit of this, the limit as x goes to infinity. So if we wanted to take a look at that, would be looking at the end behavior of the function, potentially looking for asymptotes. Okay, if we take a look at the limit of this as x approaches infinity, we're going to get something of the form infinity minus infinity, which is one of our indeterminate forms. And we've dealt with indeterminate forms of this type previously in the course, where algebraically we can investigate it by multiplying by the conjugate of this over itself. We wouldn't do that if we had something like infinity plus infinity, because of course that would not be indeterminate. Infinity plus infinity would just be infinity. But this would be infinity minus infinity as x is going to infinity. Okay. What about x is going to negative infinity? Well, first let's check the domain of this thing. Okay. Can x go to negative infinity? Is that okay? And if that's in the domain, okay, let's check what the domain of this function is, and let's make sure we can do that. The domain for this function, well, the polynomial part, no issues. This is all real numbers for the x. But what about this? Well, the argument x squared plus x would need to be greater than or equal to 0. This is a nonlinear inequality for us to solve. And we can solve this through, how about a graphical approach, like I did in the previous exercise, by graphing the parabola y equals x squared plus x. Or symbolically, you can do factoring. X times x plus 1 is greater than or equal to 0. And in order to solve this correctly symbolically, you would want to note where x is equal, where this would be an equation. That's where x is equal to 0, and where x is equal to negative 1. I should do it this way, right? 0 and negative 1. And you'd actually want to test within these subintervals here. Okay, because you're taking a product of two quantities, a product, right, it's not sufficient to say that x is greater than or equal to 0 and x plus 1 is greater than or equal to 0. That's not sufficient. Because this is saying that each of these is positive. If this were true, then that's forcing them both to be positive. But they don't have to be. It could also be the case that both of these are negative, because a negative times negative would also be greater than 0. And that's why this is not the way to approach a nonlinear inequality here. Okay, so we can test negative 2, negative 1/2, positive 1, and see what happens. And I'm going to do the same approach, but I'm going to do it graphically over here. Y equals x squared plus x. It has x-intercepts at 0 and negative 1. So here's negative 1, here's 0. And because the leading coefficient is positive, then this is a parabola that is face up like that. So how do I get it to go through these 2 points and have that shape? By making the curve look like this. Now if I choose values of x like negative 2, if I plug it in, graphically I can see that the quadratic is going to output a positive out there. So I already know that at negative 2, right, we're going to get negative times negative. This is positive in that region out there. Any number between negative 1 and 0 would output a negative. Just try it by plugging in negative 1/2 or something like that to this, and you're going to get that this is negative here. And any value greater than 0, this is going to output a positive. Okay, so the domain of this function, that's wherever this is greater than or equal to 0. Well, it's equal to 0 at 0 and negative 1. So the domain of the function then looks like it's going to be from negative infinity to negative 1, including the negative 1, because that's where this would equal 0. Union, okay, including the 0, because at 0 this is equal to 0, and out to infinity. So the domain of this function excludes the open interval from negative 1 to 0. There's our domain. And now this answers the question, should we investigate the limit of this as x goes to negative infinity as well as going to positive infinity? Okay, I'm going to take a look at that right now. The limit as x goes to infinity of f of x. First, the limit as x goes to infinity of the square root of x squared plus x minus x. This is going to give us, we have infinity squared plus infinity, so this is infinity. The square root of that is still infinity, right? So we have infinity minus infinity, and that is our indeterminate form. We can approach this algebraically, and we can also, in other words, transform this into another indeterminate form. 0 over 0 comes to mind, or infinity over infinity. And then we can use either an algebraic approach to that, or we can use L'Hopital's rule if we choose it. That's the way we want to go. Okay, the technique we have for transforming this, expression of this type, into that rational form is to multiply by the conjugate. If you multiply by the conjugate here, we're going to end up with x squared plus x minus x squared. That's multiplying this by its conjugate, and then we're going to multiply the denominator by that conjugate as well. These x squareds cancel each other out, and now what happens when we run this limit? The numerator goes to infinity, the denominator will be infinity plus infinity, so we now have infinity over infinity. We can now apply L'Hopital's rule to this if we want, or we can use an algebraic approach. The algebraic approach we had from previously in the semester was to divide all the terms, numerator and denominator, right, by the term that is growing the fastest in the denominator. And in this case, we have x, we have the square root of x squared, which is x, and we have the square root of x. So I'm going to divide everything by x. So we have x over x in the top. Okay, we have x over x in the denominator, but recall that x is equal to the square root of x squared when x is greater than 0, which it is. So we have inside the square root, we would be dividing by x squared, because the square root of x squared is x. Like that. And now we can run this limit. So we have this piece right here is just 1. This one right here is 1 as well. And x over x squared is 1 over x, which as x goes to infinity, this goes to 0. And x squared over x squared, that is going to 1 as well. So we're evaluating this limit. We get 1 on top. We've got the square root of 1 plus 0 and then plus 1. So we get 1/2. What does this tell us about the graph of this function? As x goes off to infinity, the function is approaching the constant 1/2. This tells us the graph has a horizontal asymptote at y equals 1/2. And it approaches it and it goes to the right. It's either approaching it from below or from above, but it certainly has a horizontal asymptote. Does the function also approach that asymptote to the left? Well, let's take the limit as x goes to negative infinity to find out. X goes to negative infinity of f of x. So we have the limit as x goes to negative infinity. Root, I'm going to call this x squared plus x is x times x plus 1, right? And then minus x. Let's take a look at this. Now, if x is going to negative infinity, right, then we have, let's see, so this is going to negative infinity, but also notice x plus 1 is going to negative infinity as well, right? And negative infinity times negative infinity would be positive infinity, and the square root of that would also be just positive infinity. Okay, so what we have, so this first term is going to a positive infinity, and then we are subtracting x, but x is going to negative infinity. So we get infinity minus negative infinity. But that's infinity plus infinity. That's just going off to infinity. In other words, it's not indeterminate when we do this limit. Okay? It's going to infinity. That is, as the graph goes off to the left, it's going up towards infinity. So we have end behavior like this in quadrant 2. As x goes to negative infinity, y is going to positive infinity. We still have to figure out if we're approaching this asymptote from below or above. Let's see, does f of x cross the horizontal asymptote of y equals 1/2? How do we know if two functions intersect? By setting them equal to each other. So we have the square root of x squared plus x minus x. We'd like to find out, can that equal 1/2? Can we solve this equation? Well, this is a radical equation. Here's a way to solve it. Let's isolate this radical by moving x to the other side. And then we can square both sides of this equation to remove the radical. So I have x squared plus x is equal to the quantity x plus 1/2 squared. So x squared plus x is equal to, this is x squared, plus 1/2 x and 1/2 x is just x. 1/2 squared is 1/4. Let's solve this. Subtract x squared from both sides, they cancel. Subtract x from both sides, they cancel. We're left with 0 equals 1/4, but that's false. So the answer to this question here is no. The function does not cross its own horizontal asymptote. Start putting together a sketch. Our horizontal asymptote is at y is equal to 1/2. Okay. We have that the function is, its end behavior to the left is like this. X goes to negative infinity, then y goes to positive infinity. All right, y goes to infinity as x goes to negative infinity was the end behavior over there. We have that it's approaching y equals 1/2 as x goes to infinity, but we don't know yet, does it go like this or does it go like that? We haven't established that. But what we do know is that it does not cross the horizontal asymptote. Okay, so it does not cross its horizontal asymptote. Okay, what is the domain, by the way, right? We said the domain was negative infinity to negative 1, including negative 1, union 0 to infinity, where we're including 0. So it does not exist between negative 1 and 0. The function does not exist in here. The question is, it does exist at negative 1, it does exist at 0. Where are those points located? Let's find them. What is f of negative 1? For instance, that would be the square root of negative 1 squared plus negative 1 minus negative 1. Right? So square root of 1 minus 1 plus 1, so that's just equal to 1. So the point negative 1, 1. Well, if this is 1/2, then 1 would be maybe up here, right? So there's a point that exists right there, and that's the point with coordinates negative 1, 1. It does not exist between negative 1 and 0. But what happens at 0, where it is in the domain, right, at the endpoint of a domain? Well, f of 0 would be the square root of 0 squared plus 0, and then minus 0, right? That's just 0. So we're talking about the origin then, right here. Okay, so we have that the function exists at the origin right here. We have that it approaches this horizontal asymptote. Maybe it does something like this. But it's also possible it could do something like this. How would we know? Let's see if we can find any x-intercepts. All right, maybe that would be useful to know. It would also, another way that we could find out, by the way, if it did something like that, okay, would be to check to see how it is increasing and decreasing. If it's not decreasing, if it's only strictly increasing over here, then it can't do this. What about concavity? Well, if it does something like this, if it just nice and smoothly curves over like that towards the asymptote, it's going to be concave down over that entire interval. If it does something like this, right, then we're going to have changes in concavity within this interval, right? So we can check by use of the second derivative for concavity, and we can check with the first derivative for increasing and decreasing. Okay, but if the x-intercepts are not hard to find, then we can also determine right now whether this crosses the x-axis, if that's even a feature for us to consider. All right, so we would set the function equal to 0, so 0 equals the function, and we can try and solve for x. X equals the square root of x squared plus x. Square both sides, we get x squared equals x squared plus x. So that means that subtracting x squared from both sides, 0 equals x. That's the only x-intercept. It's the same as the y-intercept. The only x-intercept. That tells us there are no more x-intercepts out here. That means it is not possible for it to do something like that, because it would cross the x-axis. So we've ruled out it being able to go down here into quadrant 4. It can't do that. We already know that it's not going to go down here into quadrant 3 as well, because it exists here, and it does not cross the horizontal asymptote. I mean, it still could do stuff like this. We have to check increasing, decreasing, and concavity in order to establish that. But the simplest possibility is this, that maybe it goes off like that, and maybe it does this to approach this asymptote. That would be the simplest possibility. And if that was true, we would find that it is decreasing over here, but increasing over here, right, exclusively. And we would find that it is only concave up over here and only concave down over here. That's how we're going to know for sure whether that's really the shape that this function is going to take. So let's look at the derivatives then to establish that. Let's see how is increasing, decreasing, maxima, minima. Let's establish all those things. All right. I think we've already established that this point right here has to be the minimum, the absolute minimum. It's not a local minimum because it doesn't exist to the left, but it looks like it's absolute because we've established, because this can't cross this asymptote and because this doesn't cross the x-axis, it does not exist down here and it does not exist down here. So I think we've already established then that this is the absolute, okay, the absolute minimum is that point right there. Okay, that's where the y value is 0. Not local minimum, right? Because we cannot move, we cannot test to the left of it. So it's not a local minimum, but it is the absolute one. All right, but to check all these, we should look at the derivative, right? First derivative. So derivative of root x squared plus x and then minus x. Derivative of a square root is 1 over 2 times that square root. And then we have to apply the chain rule. So we need to multiply this by the derivative of x squared plus x. Well, that would be 2x plus 1. That's a chain rule. Derivative of negative x is minus 1, right? This right here, right, was a chain rule, right? All right, well, there's our first derivative. Now we should establish the critical values, okay? Let's look where it doesn't exist. F prime of x does not exist if this denominator is 0. So that would be anywhere where x squared plus x is equal to 0. That would be where x times x plus 1 equals 0. So f prime of x does not exist if x is equal to 0 or x is equal to negative 1. Right? But those were endpoints. Those were closed endpoints. Those were endpoints in our domain. All right? We already know what happens at those points. They are endpoints, and we've already included them on our graph. Okay, we're not going to test between them. Right? We're going to test, though, to the left of this one and test to the right of this one. So that's important to consider. Now, anywhere where f prime of x is equal to 0, well, that means we should set 0 equal to this, 2x plus 1 over 2 root x squared plus x minus 1. And let's see what solutions we can find to this, if any. So 1 equals 2x plus 1 over 2 root x squared plus x. Multiply the denominator over to the other side. So 2 root x squared plus x equals 2x plus 1. So I'm going to square both sides of the equation and remove the radical. So that gives us 4 times the quantity x squared plus x is equal to 2x plus 1 quantity squared. 4x squared plus 4x is equal to, expanding this, we get 4x squared. 2x and 2x is 4x and then plus 1. We can subtract 4x squared and 4x from both sides. We get 0 equals 1, but that is false. What did we just find? Okay. There are no points, okay, no points such that f prime of x is equal to 0. In other words, there are no horizontal tangents. The only critical values then are 0 and negative 1. Okay? We're not going to test between 0 and negative 1 because that would not be within the domain of the function. Okay, so here's our domain. Negative 1 is a point that's included, right? 0 is a point that's included, okay? But in terms of the first derivative, does not exist at either of these. Okay, and we're not testing it all in here, right? Because this region right here is not in the domain of the original function. So we're going to test out here, like at negative 2 we'll test, and out here at 1. And let's test that in the first derivative. So f prime of negative 1, okay, we'll find out what that is, and then we already know that one, right? F prime of negative 2, I'll color code this, okay, we have this and this. Those are the important values to test around. Okay, f prime of negative 2. Okay, so let's import our derivative now. So our first derivative is this, 2x plus 1 over 2 root x squared plus x, and then minus 1. Okay, so f prime of x is 2x plus 1 over 2 root x squared plus x minus 1. Okay, so we can plug negative 2 into this. The numerator, if we plug x is equal to negative 2, we're going to get what? Negative 4 plus 1, that's negative. Right, well, let's just evaluate it. Right, it's not that hard. We don't have to do this for 2 numbers. So negative 4 plus 1 is negative 3. Okay, and then the denominator, we have 2 times what is going to be a positive quantity here for sure, right? Negative 2 squared is 4, and then minus 2, and then minus 1. Okay, so we have negative 3 over what? 2 root 2 minus 1. Well, notice this is a negative minus a negative, so this is going to output something negative. So the second derivative is negative at negative 2. So that means that the function is therefore decreasing. It's going to be decreasing within the open interval, that is, from negative infinity to negative 1. Right? Remember, negative 1 itself is included within the domain of the original function, but negative 1 is not in the domain of the derivative. And now let's test at 1. So f prime of 1. So that's going to give us 3, positive 3 for the numerator. The denominator is going to be 2 times the square root of 2, and then minus 1. Okay, so now we have 3 over 2 root 2 minus 1. So we have a positive, minus, and negative. So let's investigate a little bit further. Well, the square root of 2 is between the square root of 1 and the square root of 4. That is, it's between 1 and 2. In fact, it's about 1.4. It's between 1 and 2, right? But it's certainly less than 3, but it's in fact about 1.4. Okay? Let's use that approximation. If the square root of 2 is approximately 1.4, then 2 times the square root of 2 is approximately going to be around 2.8, but it's certainly less than 3 because the square root of 2 is less than 1.5. So if this is less than 3, then this fraction right here, this fraction is therefore 3 over a number less than 3 that is greater than 1. So a number greater than 1 minus 1 is going to give us a quantity that is positive. So the first derivative is then positive here. We can check that certainly on your calculator what exactly this is, but it's going to be a small positive number. So it is increasing on the interval, open interval from 0 to infinity. Now this confirms what we were hoping to see. Right, we have that it is strictly decreasing over here, but strictly increasing here. Okay, so let's include that information. We have that it's increasing over here. We have that it is decreasing over here. Okay, and it doesn't exist. All right, it doesn't exist between negative 1 and 0. So it does seem more reasonable then that like this is not going to do, we already know this is not going to do something like this, because then it would have to increase, and we would have found more critical values if that was the case. We know it is strictly decreasing, so it seems likely that it does something like this. Is it possible to change concavity? Yes, it's still possible for it to change concavity. Could have something like that. That's decreasing throughout this whole interval, but we would have then concave down and then concave up. That is a possibility. So we still do need to look at concavity. Over here it's increasing, so it's most likely it's going to be something like that. But that would, if it is like that, then we're going to get all concave down. And again, it is possible to have change in concavity even though it would be strictly increasing over there. Okay, well let's take the second derivative then. F double prime of x. Okay, we got the derivative of this, right? 2x plus 1 over 2 root x squared plus x minus 1. All right, well, the derivative of the minus 1 will just be 0, so that'll go away. So we need the derivative of this by the quotient rule. So we get low d high. So we take the lower function times the derivative of the numerator. The derivative of this numerator would just be 2 minus high d low. So we take the higher function, 2x plus 1, times the derivative of the denominator. Okay, a derivative of 2 root x squared plus x. Well, we can factor out the 2, right? And then the derivative of the square root of x squared plus x, I think we did that before. That's going to be 1 over 2 root x squared plus x times the derivative of x squared plus x. So we're going to get a 2x plus 1. Okay, so we have low d high minus high d low, right? There's that factor of 2 there. Okay, this is d low, and then this is all divided by the denominator squared, right? And then we have like a plus 0 or a minus 0 if you wish out here, for the derivative of 1 is 0. Denominator squared is going to be 4 times the quantity x squared plus x. There's our second derivative. Let's see if we can clean this up. So we have, let's see, these 2's will cancel each other out. We have 2 times 2 here, this is a 4, so I get 4 root x squared plus x. Denominator is 4 times the quantity x squared plus x. And then here, what do we have? We have minus, we have 2x plus 1 times 2x plus 1, so 2x plus 1 quantity squared over root x squared plus x. So we have a complex rational, or a complex expression is what we have. We have fractions inside of fractions. So I'm going to cancel out this right here. I'm going to multiply through by root x squared plus x to cancel this. That means we're going to have to multiply both of these by that. And we have to multiply the bottom by this as well. That's x squared plus x to the 1/2 power to combine with x squared plus x to the 1st power. By distributing this to these terms, first we're going to have 4 times root x squared plus x times root x squared plus x. So 4 times the quantity x squared plus x minus, here we're going to get cancellation. So we're going to get the quantity 2x plus 1 squared. And in the denominator we have 4 times the quantity x squared plus x, which is then going to be to the power of 3/2. And so there's our second derivative. We can simplify further through expansion. 4x squared plus x minus, and this foiled out would give us a 4x squared plus 4x plus 1. Okay, denominator remains the same. Now we can combine the terms in the numerator. We have 4x squared minus 4x squared. Those will cancel each other out. X minus 4x gives us negative 3x. And then we have a minus 1 as well. That cleaned up pretty nicely. So we have 4 times the quantity x squared plus x to the 3/2. All right, f double prime of x therefore does not exist whenever the denominator is equal to 0. That would be where x is equal to 0 and x is equal to negative 1, as was already the case from before. And those, of course, are values that are not in the domain of the original function f. We should still test around them. Recall, we're not going to test between them because values between these two are not in the domain as well. But we should test around them. And we have that f double prime of x is equal to 0, okay, is equal to 0 if negative 3x minus 1 is equal to 0. Add 3x, okay, to this side, divide by 3. So that would be when x is equal to negative 1/3. So these are our critical values of the second derivative then. We're going to want to test around those. So we have negative 1, we have 0, we have negative 1/3. So here's negative 1, here's negative 1/3. I'll put 0 right here. Okay. Again, all right, the second derivative does not exist here. The second derivative does not exist here. And this is telling us the second derivative is equal to 0 here. But x equals negative 1/3 is not even in the domain of f. The function doesn't even exist here, right? So there's nothing to check. Right? So there's nothing even to check there. So the only places for us to check concavity would be within these two subintervals out here at negative, so left of negative 1, so let's say at negative 2, and to the right of 0, so let's say at 1. So let's check there. F double prime of negative 2. Okay, here it is right here. All right, here, I'll write it down here again. F double prime of x is negative 3x minus 1 over 4 quantity x squared. All right, x squared plus x to the 3/2. Okay. Now, the 3/2 power guarantees we're doing a square root here. So the denominator, as long as we're within the domain for this function, the denominator is going to be positive. Doesn't matter if we plug in whatever number from the domain. The The denominator is going to be positive. The numerator, though, when we plug negative 2 into the numerator, we're going to get 6 minus 1, which is positive. So the second derivative is positive at negative 2. Therefore, the function, since we're talking about second derivative now, the function is therefore concave up at negative 2, and hence it is concave up on the interval from negative infinity to negative 1. That is an open interval. No change in concavity there. Now testing the second derivative at 1, the other test value we have out here. Again, our denominator is going to be positive no matter what. Okay, you can see that. And the numerator, though, in this case will be negative, 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 right? So we got a negative there. Negative over positive is negative. So our function is therefore concave down on this interval. It is concave down on the interval from 0 to infinity. That is the open interval, right, from 0 to infinity. It's entirely concave up to the left of negative 1. It's entirely concave down to the right of 0. Let's go back to that little quick sketch we were doing over here. All right. So we found that this was concave up until we get to negative 1. And then it doesn't exist between negative 1 and 0, and then it becomes concave down from 0 out to infinity. Right? And we had that it was decreasing from negative infinity to negative 1. We had that it is increasing from 0 to infinity. So we can put the pieces together. All right, it is going to decrease and be concave up, and then it's going to hit this point which exists, but then it's not going to exist within this open interval here. And then it's going to exist again at this point right here at the origin. It's going to continue out, increasing and concave down as it approaches our horizontal asymptote like this. Okay, so there's our sketch, okay, for this function then. Okay, so we can, we can express all this information. We have increasing, decreasing, for instance. It's just listed. Our function is increasing on the interval from 0 to infinity. That's an open interval. Our function is decreasing on the open interval from negative infinity to negative 1. Okay, concavity. Our function is concave up on the interval from negative infinity to negative 1. Our function is concave down on the interval from 0 to infinity. That's an open interval, right? These are open intervals. Notice that these intervals, these are open. How about maxima, minima? We found there was an absolute minimum at 0, 0. The function goes up to infinity in quadrant 2, so there is no absolute maximum. What about local? There were no points where the derivative was equal to 0. Any local minima? This is not a local minimum because we can't test right to the left of it. The function doesn't exist there. This is not a local minimum because we can't test to the right of it in an open interval. So neither of these are local minima. Local maxima, none of those either. So no local minima, no local maxima. How about inflection? We have concave up over here, concave down over here, but we don't have a point on a continuous curve where it transitions from concave up to concave down or vice versa. Okay, so we have no local max, no local maxima or minima. All right, how about inflection? For this function, there is no inflection point. Asymptotes, asymptotic behavior. We have a horizontal asymptote at y is equal to 1/2. There is no vertical asymptote or any other type of asymptote in this graph. Okay. domain. Negative infinity to -1, including the -1, union, include the 0 out to infinity. That was the domain. Okay. The look of the graph here. Which one was this? Right. E, letter E. Okay. Here's the graph that I get from a graphing utility. Looks pretty close to the graph that we're able to sketch. Not bad. All right. Anything else? Was it even, odd, or periodic? Well, we take a look at the graph to see. It's not even. It's not a reflection over the y-axis. It's not odd. We rotate it by 180 degrees. It doesn't overlap itself. It's not periodic. It's not repeating over regular intervals. We can see this one. This would be a periodic example right here. You could use periodicity on this last example right here so that you can investigate one period. The period of the sine function is 2 pi. You could investigate one period of this function sine cubed of x to graph it over that one period, and then you can repeat that. You can also use odd symmetry on this. That is that you can choose the period to be from -pi to +pi to graph, but on that interval from -pi to +pi, because this function's odd, you can just look at 0 to pi. Right? You could investigate for sine cubed of x. You could ultimately investigate what does it look like just from 0 to pi, and we would get from this point to this point. This is the curve you're going to get through all that analysis: increase, decrease, concavity, inflection, maxima, minima, all that stuff. From 0 to pi, you're going to get this lump right here. And by odd symmetry, you can then rotate that lump around to say, but a copy of that would exist right here. And then you would have the function from -pi to +pi. And then because of periodicity, you can take that entire form and then you can repeat it again and again, and you can both directions, and that's how you can get the entire graph. But you can just look at a piece of it and use symmetries in order to find out what the rest of the curve would have to look like. Right, and for your homework, you have a variety of different examples. Now, when you look at the homework in WebAssign, it's going to do what WebAssign does. It's going to ask you to sketch a curve using the guidelines. Open that up, you get Stewart's guidelines. But it only asks you to just choose the correct graph. It's such a minimal amount of, I mean, you could finish this homework assignment in less than 10 minutes if you really wanted to, but if you're really analyzing these functions graphically according to the guidelines of this section, it's considerably more time consuming than that. So you give yourself a few hours in order to practice this. I give you, a couple polynomial ones to try. I give you a few of the rational types. Okay, in this one, you might notice if you take a look at the graphs, there might even be a removable discontinuity we dealt with earlier in the semester. You take a look at the function. This one has a few asymptotes in it, right? It looks like a couple vertical ones and a horizontal one. Here's one that doesn't have any vertical asymptote at all. Right? It's kind of a an impulse function, okay, or kind of like a Gaussian curve. Right, so when you have a term like x to the 1/3, that might suggest there's what kind of feature on the graph, as we've already seen. This is an interesting looking one here. Which one of these interesting shapes is this? Okay, one with an exponential function in it. This is like a logistic growth kind of a function. That is one that might be used to model population growth that starts out as exponential type growth, but then approaches some carrying capacity because of restrictions within the environment. So it sort of looks like it's exponential growth, but then there's a restriction that happens, and so the rate of growth slows down and it approaches that carrying capacity. Okay, and another exponential trigonometric one. All right, so always have to include, you have to take derivatives of things like exponentials, logarithms, and trigonometric functions as well. All right. Okay, I have another worked out example here in the type notes that I did. Another one I thought was interesting, which is this 1 over the natural log of x function, constructing its graph piece by piece. Right. All right, so take a look at the type notes. Take a look at Stewart's guidelines as well. Take a look at your worksheet and your homework. Let me know if you have any questions. And take care.